Hi everybody, welcome to the last video in this quiz math section 11.1 Introduction to Trees. Again, it's just an introduction, so we will briefly go through the terminologies, and then of course you should read the note carefully. Right, trees. A tree is connected undirected graph with no simple circuit, so we cannot have a circuit. And they have to be connected, meaning that you cannot have two separate parts of the graph. Of course, we have the focus to have no simple circuit but not connected. Each of them is a tree, so that's forest, very less common term. So which one of these are trees? So this one is a tree because it said no circuit, no would not consider a loop upon, but the loop is add to itself, but we defined tree is when they have no circuit. Right, this one, of course there's no circuit, but this one is not a tree because there's a circuit. If you look at it this way, yeah, you can just go in the, I'm not saying the loop, but you can go between those points, and that is a circuit, so that's not a tree because there's a loop. I'm not saying the loop, but the circuit. And then this one is not connected, the AF completely different, is not drawn to the rest of the part, so this is not a tree because it's not connected, so we have to have connected with no simple circuit. An undirected graph is a tree if and only if there is a unique simple path between any two of its vertices. So there's another application. So a tree is who can go from one point to any other point. Of course, if we start from this point, we cannot. Yeah, if there's a unique simple path between any two of its vertices, a unique path. This is not unique from A to D. For example, you go straight and then, or you can go that direction. Right, so that's why it's not a tree. Right, next, a tree are used to model computer science, chemistry, biology, but different time you can read. So that's formula, chemistry model, and then this shows the hierarchy of things. Or in a company, or the structure of a company. Right, so rooted tree. Rooted tree is a tree with one vertex has been designated as the root and every edge is directed away from the root. So here we have everything away from A, everything away from C. Right. Right. So more terminology. For rooted tree is usually from the botanical theology. So in the next page we have the family tree of the Bernoulli families, probably the most famous family in mathematics, in mathematical world. Right, and the next one I'm just going to introduce the parent is something that is coming out from it, and then the child, siblings, ancestor, all of them defined the same way. A vertex is root with no children is going to live, so the end point like this is going to live. Vertices that have children are called the internal, so those are the internal knots. So the terminology are very straightforward. Right, let's see how it works. Of course, like I said, we have the family tree Bernoulli product. Right, now just some terminology. The parent of C, that will be B. The children of G, H, I, and J. The sibling of H, B, I, and J. Ancestor of E, B, C, B, and A. Descendant of B, B, C, D, and E. And internal doesn't have leaf, B, C, A, G, H, and J. Sorry. B, C, A, G, H, I, H, A. Right, so that's all. Next we define M array rooted tree. So we define that if every internal vertex has no more than M children. So, and M is a number. So for example, this tree, this is a 2 array because every internal one have at most 2 children. So that's 2 array tree. And this will be 3. Every internal pole have no more than 3 children. This have 5 children, and this one at most will be sometimes 2, sometimes 3. So there will be 3 array. And we have some more theorem. A tree with n vertices has n minus 1 edges. A full M array tree with I internal vertices has that number of vertices. Then we have other theorem, right? And then we define that an M array tree of height h is balanced if and all the leaves are at level of h or h minus 1. Right. So this one is balanced. This one is not. It have too many levels of the leaves. And this one is balanced. And finally, we have an example. There are at most m to the h leaves in any M array tree of height h. Right. So with that, we cover everything we need for the discrete math. The last few sections is just an introduction. When we get to higher level, then we'll for more detailed calculation on those. But for last time, thank you for watching.